Okay, hello. This is my video for our next assignment in the semester project we've been working on, our wind tunnel projects. And this is assignment calculate steps numbers 5 through 7. And so to start out with assignment number 5 or step number 5, you wanted us to review the YouTube links that you had provided in the assignment link and watch those videos and look at this information, the student information here that was given to us. And so looking at the student information here, we can see that this is some of the information that you collected while you were filming your videos that you gave us. And so I'll first kind of just talk about what I thought was cool in each video and what I learned, and then we can come back and kind of look at the data here that you collected during that process. And so the first video that you had us watch here was called Airflow Measurement. And in this video, this was basically just how you set up your airflow chamber or your flow chamber, and how you took your initial readings that kind of gave you your baseline, something you could compare to when you were actually putting items into your chamber. And so it was pretty cool to watch. I really liked the plexiglass airflow chamber you'd created. It's one of those assignments where it would be really cool for an in-person class to be able to be hands-on with it and be able to watch you perform the experiments, but the videos worked out really well too. But anyway, basically this video, after you got your airflow chamber set up, what you did was take 3 velocity readings in each corner of your chamber, and then you were able to average that. And you also talked about how it was important to turn on your box and let it stabilize so you were getting accurate readings. And so that's what this first video was about. And then the second video here, you placed this box in front of the intake of your airflow chamber, and you called that the water flow chamber. And I'm not sure exactly how that works, but basically you could restrict the intake from that box going into your airflow chamber, and then you could take measurements from that to compare as well. And so similar to the first video, you took 3 readings in each corner and stabilized the velocity, and then took an average of those readings in each corner. And you did that for different positions of your water flow chamber, and so you were able to get an average velocity at different restrictions in each corner. And then the next video here is when you actually started putting items into your chamber and taking measurements of them. And so this video here was the sphere that you started with. And the video just kind of explained how you tipped your chamber on its side and then suspended your cylinder using fishing line and rubber bands. And then once your sphere, was suspended, you took a force sensor and clamped that to the side of your box. And then when you turned on your fan, the air pushing on the cylinder would give you a force reading on your force meter. And so what you did on that was similar to when you took your baseline readings. You did it 3 times and then took an average of those to get the force on that sphere, and then you could use those readings in future calculations. And then the next video here, you repeated that same process with a cylinder. And on the cylinder, once you had it suspended using the fishing line and rubber bands, you actually did it in 2 different positions for 2 different cross-sectional areas. And so the position it's in now is like the cross-sectional area of the cylinder where you're looking at the circular part. And then if I go further on in the video here, we can see that you turned the cylinder, and so the curved part of the cylinder was facing the fan. And so Then you just repeated the process that you did with the sphere, taking 3 readings, clamping your force sensor to the side of the container, and then getting an average reading by averaging what your force sensor told you. And then the last video here was another shape, and in this shape you had a block or a rectangle, and basically similar to the cylinder, you did it for 2 different areas. So the 2 different cross-sectional areas gave you different readings that we can use in our calculations. And so you took that sphere, or the block, and suspended it here using the rubber bands, and then you tried to level it using 4 different fishing lines. And then for each cross-sectional area that you wanted to calculate, you took 3 measurements using your force sensor, and then once again took an average of those. And so that's basically what the videos were summarizing, just the different shapes and getting the measured data that we can use for our project. And so if I come back here to what we were looking at the beginning, the information that you gave us, we can see the velocity readings and the measured data that you received. And in the data, there's also a golf ball in here, as well as the 2 different cross-sectional areas of the cylinder and the 2 different cross-sectional areas of the block. And so that was all for step number 5. Okay, so this is my work for step number 7, which is the last part of this assignment. Calculate steps 5 through 7. And for step 7 here, we were supposed to create a linear function using the measured force data versus velocity for each profile. And so I decided to use MATLAB for this because after I created my linear functions, I would be able to actually graph them and be able to see and compare the different shapes. And this, using MATLAB, also helped me to be more organized in my approach and be able to see things a little more clearly, to be able to compare the different shapes. And so the first thing I did was just input all of the information, the measured information that we were given. So that's what this first section is here. It's probably easier to see over here. But yeah, this is the velocity and then the drag, the measured drag for each shape, so our measured forces. And then from there I used PolyFit to accurately fit a line to this data. And then right here I put a 1 in, so we're getting a linear function because we didn't want an exponent on there, so that's what that 1 is. And so this right here is those functions. So these are the coefficients for those. We can look at and kind of compare. And then what was cool about using MATLAB for this is I was able to actually graph each of the 6 different profiles from these shapes and compare them. So this is the work that I did to plot that and then create a title and label our axis. And so if I push run up here, we can see that this is the plot of each velocity versus drag. And so each of these lines is a linear function of the measured force data versus velocity. And then the legend here shows that we have that function for each different profile or shape. And so it's kind of interesting to look at these and see the variation here. They all start at different places here, and then from there they all increase. So drag increases with velocity. But it's pretty cool to be able to see the graph there and compare those. So as far as the discussion requirements for this assignment, my group has actually been discussing back and forth for the past few days. Dylan Kitchens and I have been, messaging and talking together and kind of trying to figure out how to calculate steps 5 through 7 and kind of comparing what we saw in the videos, and we tried to interpret the results we saw and kind of compare the measured and calculated values together. And so we've been messaging and talking quite a bit. As far as other groups, we've actually been discussing with 2 other groups for this assignment. We discussed with Darrell White's group and as well as Noel's group. And you can see those discussions. Those were in the discussion sections for our class. They're all there, but we kind of posted some of our results and kind of talked about what we found out and how we interpreted them as we compared the measured and calculated values, as well as the linear functions that we created. And I shared the picture of the graph that I created, which I'll show you in just a second for part 7. So it's actually been quite a bit of discussion to try and work out what the assignment was, and also comparing our results and discussing the meaning of those results together. And so as far as step number 6 on the calculate assignment, for this part we were supposed to find the calculated force in for each of these shapes. So this is your data that you gave us here, and you can see there's the 6 different profiles here with the block, the cylinder, the golf ball, and the sphere, and then the given information, so we could calculate the areas from that, as well as we use the masses. And then those are your measured data for each shape, for each velocity. And so what I did to calculate this was I actually, in the book, I was reading through chapter 14 here and trying to figure out how to calculate that drag force. And for our situation with the airflow tunnel, we know that it's similar to this helicopter case here, where the velocity, we assume the velocity A of the air particle as it approaches the blade is 0, so we can cross out VA. And so what I did was use this equation here for the sum of the forces equals dm dt, and then I canceled out VA like I talked about there. And so this is the paper here that I did all of my calculations on, so you can see there's that equation from the book that I talked about. And from the book I know that this term here is in kilograms per second, and after messaging you, you informed me that the dm dt is also the same as the air mass flow or the mass displacement, and that's what we calculated in the previous assignment. And so using that same formula, we're able to calculate this term here and then multiply it by the velocities. And so these are the velocities that you gave us here. And if I can zoom out here, this is the table that I created here with those different values. And then taking these values that I calculated, I could compare them, my calculated values with your drag values over here. And for the most part, they were pretty similar. I think most of them were accurate within 2 decimal places at least, and quite a few of them were out to 3 or 4 decimal places. And so those were pretty accurate for you know, the amount of variation that can come from the actual experiment. So is some expected difference there, but overall I was pretty impressed with how accurate it was. And so now I'll show you my work for part number 7.